So hello everyone, myself Harshal Gorde. I'm from BITS Pilani, Pilani campus, and I'm doing mechanical engineering there. My project is surrogate modeling of the biofouling process. So as they explained what is biofouling is and all. So our temperatures are higher, our metabolic activity is higher, everything that. Then our biofilms they form in like 2 to 3 days compared to 5 to 7 days in the temperate regions. So that is a big thing. And our current solutions are there was a anti-fouling paint that we were using, but it was toxic for the environment, right? So it was banned everywhere. Then, but some ships are still using that. But what currently the fleets and ship managers follow is that they just dry dock on fixed calendar schedules. But for Indian regions, that is not really applicable because our biofouling occurs very fast. Like it is 2 to 3 times of the temperate regions. So we need a proper predictive system for that. As I explained, the 5 stages, and these are like based on chemistry and biological process, but they are using different ordinal equations that we are mapping using normal calculations. I'll explain them in depth here. So the conditioning film, in that organic molecules adsorb onto the hull. They use Langmuir adsorption kinetics. That is its own differential equation. So all of them have their differential equation as you saw in this. The second one is bacterial adhesion. So the conditioning film that previously was there, the bacteria adhesion tries to adhere. Yeah. And this is where we introduce the wall shear stress. So basically, what this means is as the shear stress is directly proportional to wall shear stress. Shear stress is directly proportional to the speed of our ship, right? So therefore, the ship speed is inversely proportional to the probability the bacteria is adhering. So that is what is shown here. Now the stage 3, the bacteria now secretes a EPS matrix, and that is followed by monode kinetics. Now that is where algae will be attracted to that EPS matrix, and then this will form like a muck and visible muck. Before nothing was visible; that there were just slime layers. Now everything will be visible. This is also like this will create the weight of the ship, will add more weight to the ship. Then finally the macro fouling. This is the most important part, and this is what we want to predict, because here the exponential drag spikes up to 55%, and we want to clean at this stage possibly. So we need to create that. Yeah. So one of the fourth stages using this Liebig's law. So this equation I'll explain. So basically, in this, that is a rate of biofouling only. So this is co-limited by two terms. There is one nutrient term and there is a light intensity term. So whichever is less, it will choose that. Then we introduce the Q10 factor here. So the Q10 factor is basically after every 10 degrees Celsius to the reference temperature. The reference temperature is 20 degrees from the temperate process. So after every 10 degrees Celsius, we multiply this whole equation by Q10. And our Q10 was in general around 2 or 2.1 or something. That was from research papers that I found. Yeah, so we created a data set. Now we mapped the physics model. We had the old ordinary differential equation as a physics simulator. Then we used that to get the data set using Latin hyperscube sampling. But this data set is like default values. It is uniformly spread out. But what we want is each parameter is sensitized, like right. Each parameter has different sensitivity. So that I'll get data from his model, the parameter sensitivity, and then I'll get better model for the ML model to train, better data. And these are the 5 inputs that will generate from the data. Then I trained that data on the random forest surrogate model, and I'm getting a very good response time to that. So yeah, so some of the outputs were biofilm thickness, microfouling, macrofouling, and then drag increase, all those, right? But the biofilm thickness and microfouling were kind of failing because they form very early in the stage and they get saturated very quickly. Like in 5 days only, the whole biofilm forms. But we can't predict it because there is almost no variance in the data. So, but this is commercially irrelevant because the ships aren't going to dry dock in 4 or 5 days. They'll need like at least 90 days or something to dry dock. So our model is working very good for the 90 days parities, and it is almost working flawlessly. These are the R square values of the drag increase and macro follow densities. So I wanted to integrate this static model. So there's a static model and there's a dynamic model. I'll explain that. So the static model is basically for the ports. So what it assumes is it takes 5 inputs, and at the end of 90 days, it will assume that the ship was in this same environment for whole the 90 days and then same speed. But that is not what really happens. I'll explain that later. So I'm using the static model for MSK integration. So I wanted to create a like a heat map of where are the hotspot of biofouling and all. So what I did is I took data maps, like satellite data maps from Copernicus, and I used the surrogate model and to calculate the rate of biofouling heat map. So the inputs were sea surface temperature, then nitrate concentration, then larval supply, then solar irradiance. Solar irradiance, I didn't really need data. I just simulated it using solar zenith angle model. That is way easier to do. Then this is the heat map I'm getting. So you look that in tropic region, there is a lot more biofouling, right? But this is a lot sensitized by sea surface temperature. But then I'll get the sensitivity rank matrix from him. Then I'll know which parameter is more working, and then they'll map out properly to get a better heat. Yeah, so the dynamic model that I talked about. So the ships, they don't generally stay at a single port for 90 days, right? They move places, they have routing, they have to do stuff. So for the dynamic model, it will assume that if we will give it a timeline of the ship's route. So like at timestamp 1, timestamp 1, 2, then it will calculate the speeds. Then it will take, the model will take the environmental parameters from whatever timestamp it is there. Then it will try to calculate the final biofouling, and it will plan a schedule for you that whenever you want to remove the parts, do the dry docking and all. So the previous model was a 90-day single shot 90-day predictor. But what we want right now is to calculate day by day. Like I'll give it timestamp 1 and timestamp 2 days, and it will calculate accordingly. That is what we want, and it will show the current hull conditions, drag penalties, and it will give the cleaning schedule. It will also like give better routes, like where it should go from to avoid more biofouling. Yeah. So the current contributions are that I created the 5-stage physics simulator, then the 80,000 scenario data set. Then I trained that on my random forest surrogate to get near perfect 90-day drag and macro follow prediction. Then I integrated this into the MSP platform by creating a heat map of the biofouling data. And the opportunities ahead are to integrate live AIS and satellite data for the biofouling prediction, and try to validate this using IOR data, which will get afterward because there is no IOR data. I try to validate it using temperate region, but yeah, it works. But the thing is, temperate region and tropic region have different species and all. It's very different. So we'll need more data to work on that. Thank you.